video we'll talk about the normal and the binormal vector, okay? And those are closely related to the unit tangent vector that we talked about it yesterday in the last video. And within its name, right, it stated the fact that the magnitude of this vector is 1. Now let us recall something that we learned in section 13.2, if I'm not mistaken, and it said that if the length of a vector function is a constant, then that vector function is orthogonal to its derivative, okay? Now, t is a unit tangent vector, and in 3D it has infinitely many vectors orthogonal to this vector. But we are interested in t prime, okay? We're interested in t prime because by what is written here and by the fact that the magnitude of t is 1, that means that t prime is orthogonal to t, okay? Well, t is not necessarily a unit vector, so we defined the similar way we defined the unit tangent vector. We defined a vector n that is the derivative of the unit tangent vector over its norm, and this vector, it's called the normal vector. Okay, so the normal vector is orthogonal to the unit tangent vector because it has the same direction as t prime, and we already talked that t prime is orthogonal to t, and moreover is has length 1 because it's divided by the norm of the derivative of the unit tangent vector. Okay, so let's say we have some curve here, and then this is the unit tangent vector, then this is going to be the normal vector, where this is right angle, and you'll see in a second why I wrote it like this, because we're also going to define, right, another vector that's orthogonal to both of these, and that's the binormal vector. And how do I find a vector that's orthogonal to two vectors? Well, we do that by what? By finding the cross product of those two vectors. So if I want to find a vector orthogonal to the normal vector and the unit tangent vector, then I find the cross product. This vector b, we define it as, we call it as the binormal vector. Binormal vector. Okay, what can we say about this binormal vector? Well, the binormal vector is also of length 1. Recall that if you have the magnitude of the cross product of u and v is equal to the magnitude of u times the magnitude of v times sine of theta, where theta is the angle between the vectors u and v, okay? Then the magnitude of b, I want to show that this is 1, is equal to the magnitude of the cross product by definition of the unit tangent vector and the normal vector by properties of the cross product, that's equal to the norm of the unit tangent vector times the norm of the magnitude of the normal vector times sine of the angle between the unit tangent vector and the normal vector. Well, we talked that the unit tangent vector and the normal vector are orthogonal, so that means that the angle between those two is pi over 2. Well, from here it's obvious that the magnitude of b is 1. Why? Because the unit tangent vector is 1. We define that the normal vector with length 1, and sine of pi over 2 is 1, so obviously the length of this vector is 1. Okay, so these three vectors follow the curve on each point. Also, they're called as the T and B frame. Okay, so let's do an example. Let's find this T and B frame, which is frame, sorry, which is a trio of vectors. So the first example, T, sorry, find T and B, where R is defined as cosine of T, sine of T, ln of cosine of T. Okay, so first of all, let's find T. T is R prime over the magnitude of R prime. R prime is equal to negative sine of T cosine of T, derivative of ln of cosine of T is cosine of T times derivative of cosine of T, which is negative sine of T. So R prime is equal to negative sine of T cosine of T negative tangent of T. Okay, this question, let us just complete this question. At the point, right, at the point P with coordinates 1, 0, 0. Okay, so if you look at for what T I obtained this point on the curve described by this definition, we can say that T is equal to 0. Cosine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, ln of 1 is 0. Okay, so how much is R prime at 0? R prime at 0 is sine of 0 is 0, cosine of 0 is 1, tangent of 0 is 0. Okay, then I can find the magnitude of R prime evaluated at 0. That's just square root of 0 squared plus 1 squared plus 0 squared, and that's equal to 1. So from here, the unit tangent vector at 0 is equal to, the unit tangent vector at 0 is equal to negative sine of T cosine of T negative tangent of T over the square root of negative sine of T squared plus cosine squared of T plus negative tangent of T squared. Sorry, this is T at T. Okay, and the unit tangent vector at 0 is R prime evaluated at 0 over the length of R prime at 0. The length of R prime at 0 is 1, so I just have 0, 1, 0 over 1, which is 0, 1, 0. Okay. Now I want to find the normal vector, and the normal vector is equal to derivative of the unit tangent vector over the norm of that derivative. Okay, so how much is the unit tangent vector? Well, the question is, can I simplify this square root right here? Okay, so let's do that. Negative sine of T cosine of T negative tangent of T over the square root of sine squared of T plus cosine squared of T plus tangent squared of T. Sine squared plus cosine squared is 1, so you get negative sine of T cosine of T negative tangent of T over square root of 1 plus tangent squared of T but 1 plus tangent squared of t is secant squared. And the derivative of secant squared is just secant. Here we have negative sine of t, cosine of t, negative tangent of t. Okay. So this is t of t is equal to negative sine of t over 1 over cosine of t, cosine of t over 1 over cosine of t, and negative sine of t over cosine of t over 1 over cosine of t. Right? This is just secant of t. Okay. Okay. Now that I have the unit tangent vector in terms of t, I have to find its derivative. And that's negative cosine squared of t plus sine squared of t, negative 2 cosine of t, sine of t, and negative derivative of sine of t is negative cosine of t. Let me just make sure here. Derivative of sine of t is cosine of t, so cosine times cosine is cosine squared, plus negative sine of t times derivative of cosine of t. Derivative of cosine of t is sine of t, so sine of t times sine of t is sine squared. Negative sine of t times sine of t is sine squared. By the chain rule here I get negative 2 cosine of t sine of t, and derivative of sine of t is cosine of t. Okay, so then I can evaluate how much is t prime evaluated at 0. That's negative cosine of 0 is 1, so negative 1, sine of 0 is 0, sine of 0 is 0, so the second component is 0, and cosine of 0 is 1, so negative 1. Okay, in this moment I can evaluate the magnitude of t prime of 0, that's square root of negative 1 squared plus 0 squared plus negative 1 squared, that's square root of 2. So the normal vector at 0 is equal to t prime at 0 over its magnitude, which is 1 over square root of 2, negative 1, 0, negative 1. And finally, we just have to find how much is the binormal vector of 0, and that's equal to the unit tangent vector cross product the normal vector, which is equal to, how much was the unit vector? What did we find? 0, 1, 0, and negative 1 over square root of 2, 0, negative 1 over square root of 2, and that's equal to negative 1 over square root of 2, right? This times this minus 0, then minus, well, that's just 0, because 0 times negative 1 over square root of 2 is 0, negative 1 over square root of 2 times 0 is 0, and finally this is 0 minus this product, which is negative, so that's going to make it positive entry. So I didn't have a better choice, so I'm gonna show you something that I found in my son's toys here. So let's say that this is our curve here, okay, something like this, okay. Give me a second. And let's say that we're talking about this point right here, right? Let's say that this is the direction of the curve, okay, it goes like this. Because it goes like this, then the unit tangent vector is going to be this vector right here. And let's say that this length is 1, okay. Then the normal vector is going to be like this, okay. And the binormal vector is going to be its cross product, so it's going to be something like this. Okay. Now let's see what is the plane defined by these two vectors. What is the plane defined by the normal vector and the binormal vector, these two vectors, right? So that plane is going to go, let's say that this is our plane, okay? That plane is going to go like this. Okay? So the binormal vector and the normal vector are going to come on now, are going to lie on this plane, okay? But that means what? If the normal vector and the binormal vector lie on this plane, then this plane is what? Orthogonal to the unit tangent vector, right? Or in other words, the unit tangent vector is normal vector to this plane. So we define this plane, okay, and we call it the normal plane. The normal plane is the plane containing the binormal vector and the normal vector, okay? This means that the unit tangent vector is the normal vector or is a vector orthogonal to the normal plane. Okay, so if we have a plane like this and this is B and this is N, they're orthogonal, then the vector coming out of this plane, and we're going to represent that like this, that goes towards us, is the unit tangent vector, okay? So how do we find an equation of a plane? It's n dot product r minus r naught is equal to 0. I'm sorry, where n is a vector normal to the plane and r naught is a point on the plane, okay? So example, find the normal plane the equation of the normal plane of r of t is equal to 2 times sine of 3ti plus tj plus 2 cosine of 3tk at the point 0, pi, negative 2. Okay, so right away for this particular vector function, what t describes this point, look at the second component is just t, so t has to be equal to pi, so that means that t is equal to pi. Just confirm that everything is okay. When t is pi, sine of 3 pi is 0, so that gives us this component, good. And then cosine of 3 pi is negative 1 times 2 is negative 2. Okay, so t is equal to pi. Okay, so what do we have to do? We have to find the unit tangent vector at t is equal to pi, and then I have the point. We do this product rule and we're done. Okay, so let's do this quickly. R prime of t is equal to 6 cosine of 3t, right? Derivative of this component. Derivative of t is 1. Derivative of cosine of 3t is negative 3 times sine of 3t times 2, negative 6 of sine of 3t. Okay? So at this point, all I want to find is, they're just asking me to find the equation of the normal plane. That means that I have to find t, because t is orthogonal to the normal plane. Okay, so right away I'll find the derivative evaluated at pi, at pi. Cosine of 3 pi is negative 1, so negative 6, 1, sine of 3 pi is 0, so 0. The magnitude of r prime evaluated at pi is equal to square root of 6 squared, negative 6 squared is 36 plus 1, so that's square root of 37. Okay, and from here the unit tangent vector at pi is equal to negative 6 over square root of 37, 1 over square root of 37, and how much is this? The last one is 0. So this vector with length 1 is normal vector to the normal plane. Okay, so we can just write n dot product r minus r naught is equal to 0, can be written as, so n is, this is for any general plane. For the normal plane, this n is the unit tangent vector, negative 6 square root of 37, 1 over square root of 37, 0 dot product, and this vector here, let's say any vector x, y, z, so x minus the x component of the point, that's 0, y minus pi, and then z minus minus 2, so plus 2 is equal to 0. Let's simplify this, negative 6 over square root of 37x plus 1 over square root of 37 y minus pi over square root of 37, and then plus 0 is equal to 0, multiply everywhere by square root of 37, negative 6x plus y is equal to minus pi is equal to 0, or the equation of the plane negative 6x plus y is equal to pi. Okay, so going back here, if I have, let's say, again, this is going to be my unit tangent vector and this is going to be binormal vector and the normal vector, the plane that is orthogonal to the binormal vector, or in other words, the plane that contains t and n, the unit tangent vector and the normal vector, is called the osculating plane. And the osculating plane is the closest plane to the curve at that particular point. Okay, so we define the osculating plane is the plane containing t and n, the unit tangent vector and the normal vector. This means that the binormal vector is orthogonal to the osculating plane. Now, if you want to find the osculating plane, B is going to be that n dot product r minus r naught is equal to 0. This n basically is going to be B times r minus the point on the curve is equal to 0, the equation of the osculating plane. So let's find the osculating plane in the previous example, okay? So let's one more time recall that r of t is equal to 2 times sine of 3t, t and 2 times cosine of 3t. Okay, we found r prime, which is 6 cosine of 3t, 1 and negative 6 sine of 3t. Now, for the first example, I didn't really need to evaluate the unit tangent vector at t, but now I have to. Why? Because in order to find n, I have to find t prime. So I need to have an expression of the unit tangent vector in terms of t. So I have to find the length of the derivative of r for any t. Okay, so let's find that magnitude. That's 6 cosine of 3t squared plus 1 squared plus negative t 6 sine of 3t squared. That's square root of 36 cosine squared of 3t plus 1 plus 36 sine squared of 3t. That's equal to 36 cosine squared 3t plus sine squared 3t plus 1. This identity is 1, so I end up with square root of 37, okay? Which means that the unit tangent vector at any t is equal to 1 over square root of 37, 6 cosine of 3t, 1 negative 6 sine of 3t. And now you can confirm whether in the previous example we got the right unit tangent vector when t was equal to pi. Okay, now we want to find how much is n at pi. And n at pi is the derivative of the unit tangent vector at pi over the magnitude of this derivative. So the derivative of the unit tangent vector is 1 over square root of 37. Now let's find the derivatives here. Negative 3 times 6, 18 sine of 3t, derivative of 1, 0. Derivative of sine of 3t is 3 times cosine of 3t. 3 times negative 6 is negative 18 cosine of 3t. Now t prime at pi gives us 1 over square root of 37. Sine of 3 pi is 0, 0. Cosine of 3 pi is negative 1 times negative 18 is positive 18. Okay, and now let's find the magnitude of this. So is equal to square root of 0 plus 0, right? 0 squared plus 0 squared plus 18 squared over 37, which is 18 over square root of 37. I didn't do any mistake. And then finally n evaluated. The normal vector at P is going to be this vector here, 1 over square root of 37, 0, 0, 18 over 18 over square root of 37, which gives us 0, 0, 1, because 18 divided by 18 is 1. Okay? So based on this, I can find the binormal vector evaluated at pi. That's t evaluated at pi, cross product n evaluated at pi. Let me just make sure that how much is t unit tangent vector at pi. We evaluated that at negative 6 over square root of 37, 1 over square root of 37 and 0, and the normal vector was 1. So the binormal vector is 1 over square root of 37, negative 6 over square root of 37 times negative 1 is positive, and then the last one is this cross product here, which is 0. Now I'm going to simplify this a little bit. Remember that B is orthogonal to the binormal vector is orthogonal to the osculating plane. This is the binormal vector. But any vector parallel to this vector is also orthogonal to the osculating plane. So I can simplify my calculation, something that I forgot to do when I found the normal plane. I can simplify this calculation by finding an easier vector to deal with that is parallel to the binormal vector. And how I'm going to find that vector? Well, that's going to be any constant multiple, right? So why don't I just multiply this vector by square root of 37? Note that the vector 1, 6, 0 is also orthogonal to the It's also orthogonal to the osculating plane. Why? Because it's a constant multiple of the binormal vector. So I'm going to deal with this one when I'm going to, so I define this vector n dot product x minus, what was the point? At what point we were looking at this? X minus 0, y minus pi, z plus 2 is equal to 0. Right? Now this vector n is not a unit vector, right? It doesn't have length 1, but that's not necessary when we're looking for a vector orthogonal to particular plane. Okay, so I have 1, 6, 0 dot product x minus 0, y minus pi, z plus 2 is equal to 0. That's x, 1 times x is x, plus 6, y minus 6 pi, plus 0 is equal to 0. Or finally, x plus 6y is equal to 6 pi.